Thanks everybody for coming and welcome to the Oxford Climate Research Network annual lecture. So the Oxford Climate Research Network is a network that exists for all those people at the University of Oxford who have a research interest in climate. And it acts to connect us up, allows us to take advantage of opportunities, makes us more than the sum of our parts. It also acts to raise our profile, both in the wider university and, of course, outside of Oxford. So we currently have about 200 people involved in the network. We run events at least once a term, and we share opportunities and details of opportunities related to climate, news and events in a weekly email digest. So if you're not already signed up on our mailing lists, then please do get involved. And the way to do that is to email ocrn@earth.ox.ac.uk and just let us know. The main event in the OCRN calendar every year is an annual lecture from a distinguished visiting scientist. In the last few years, those have taken place online. And so I'm thrilled that we can actually be here in person to welcome this year's speaker. So I'm going to hand over to Steve Smith, who knows Kirsten better, to introduce our speaker.
Thank you very much, Helen. Hello, everyone, from me as well. It's a real privilege to be able to welcome Dr. Kirsten Zickfeld to give the OCRN annual lecture this year. As you can see, Kirsten is Distinguished Professor of Climate Science at Simon Fraser University in Vancouver, Canada. Among many of the things she's done, she's contributed as an IPCC lead author to the most recent 6th assessment report, also to the special report on 1.5 degrees C. And she's received many awards for her work, which has tended to focus on very long time scales of the climate system and the implications of what we do now, and the implications of our CO2 emissions in particular, and the irreversibilities of what we might be doing to the climate now. Here at Oxford, of course, we're rightly very proud of Professor Miles Allen, and often gets referred to as the scientist behind net zero. I think maybe Kirsten has a pretty good claim to that title as well. There were a very small number of climate scientists in the sort of early 2000s, 2009, who were cottoning on to the fact that if you look at the way the climate system behaves in a really holistic manner, looking at the way carbon cycles around the Earth and also the climate response to that carbon, you see this strikingly linear, close relationship between total CO2 we put into the atmosphere over all time, our cumulative emissions, and particularly peak temperature. From that, we get the idea of a cumulative CO2 budget. And from that, we get the idea that if we want to actually limit warming to any level, we really need to get to a point where any further emissions are balanced out by removals, hence the concept of net zero. So Kirsten's really been formative in developing that concept, and then, of course, explaining it and socializing it through IPCC reports and so on. So as a researcher myself in the field of carbon dioxide removal, I've certainly been learning from and citing Kirsten's work over several years now. So I'm really looking forward to this lecture. I hope you will join me in welcoming Kirsten and listening to what she has to present. Thank you, Kirsten.
Thank you for this very kind introduction. It is an honor to have been invited to deliver this lecture today. So as my slide shows, I will talk about carbon dioxide removal, specifically its effects on climate and the implications for net zero. So as a climate scientist, I will speak largely about the climate science aspects of carbon dioxide removal, but also address some of the motivation for looking at this concept and also some of the implications. So why carbon dioxide removal, or CDR? The main reason, so as we heard, is that our remaining carbon budget to stay under a given amount of warming is relatively tight. So any additional emission needs to be counterbalanced by removal from the atmosphere. And for these reasons, carbon dioxide removal is a key measure in scenarios that are consistent with the goals of the Paris Agreement to limit warming to 2 degrees Celsius while pursuing efforts to limit warming to 1.5. So this figure here shows an illustrative scenario that is consistent with limiting warming to 1.5 degrees. So if on the vertical axis, we have greenhouse gas emissions, and then as a function of time. And these green areas here below the zero lines, this is the amount of carbon dioxide removal that is implied in this type of scenario. And carbon dioxide removal has, I would say, perhaps 3 main functions in scenarios that get us to net zero. So first of all, we need carbon dioxide removal to accelerate decarbonization, or to get us on a trajectory where net carbon dioxide emissions are reduced. In these scenarios, carbon dioxide removal is also needed to compensate for emissions that are difficult to remove. Those are those associated with transportation, so emissions from the aviation sector, but also from agriculture. And then if you look later this century, you will see that the net emissions, which is the balance between emission into the atmosphere and removal, also drops below the zero line. So there's this, the dashed line here, this is net zero, net CO2 emissions. So that is the balance between CO2 emissions and removals, whereas this solid line here, this is net greenhouse gas emissions, so this also involves the other greenhouse gases. And what you see here, that in the second half of the century, these lines drop below zero, reaching net negative CO2 greenhouse gas emission, which is needed to bring us down from a temperature peak. And what you can also see in this figure here is that currently there is already some amount of carbon dioxide removal that is used. These are the more conventional methods, so things that we have done for decades to millennia, such as managing our land sector. But as we move forward in time, as is indicated by this light green line, we will also need more novel carbon dioxide removal technologies. So how can we remove carbon dioxide from the atmosphere? There are different categorizations in the literature. Here I will use the one from the latest IPCC report, where CDR methods were categorized by removal process. So this is indicated by these gray boxes here. So we can remove carbon dioxide from the atmosphere through biological processes. So for example, photosynthesis and net primary productivity by plants, which remove carbon dioxide from the atmosphere and store that in biomass. So we can do that on land or in the ocean. Then there are geochemical methodologies. So these harness chemical reactions in the Earth system. So those that are usually involved in the long-term sink of carbon dioxide, such as, for example, ocean alkalinization. And then finally, there are methods that are here characterized as chemical, which is using chemical procedures to remove carbon dioxide from the atmosphere and then store it underground. And one example of this technology would be, for example, direct air capture. So sucking carbon dioxide out of the atmosphere, separating the carbon dioxide with through a chemical process, and then storing that underground. These technologies or these methodologies have different storage timescales. So this is indicated by these colored boxes here. In some cases, the storage timescale is relatively short. This is when the carbon is sequestered into the short-term carbon cycle. So that would be biomass or soils. And then up to geologic timescales of tens of thousands or a year of longer, which is when the carbon dioxide is sequestered into geologic reservoirs. So what I would like to do in my talk here today is talk about how the carbon cycle responds to carbon dioxide removal. So carbon cycle science has focused very much on increasing carbon dioxide concentrations under rising emissions. And in these scenarios where carbon dioxide comes into the picture and eventually may result in net negative emissions, we need to understand how the carbon cycle responds to removals. And then I talk about how can we quantify the effectiveness of carbon dioxide removal. So the question is, if we take 1 unit of carbon out through one of the methods that I have described, how does that affect the atmospheric CO2 concentration and warming? And then I'll talk a little bit about asymmetries in the response of the Earth system to emissions and removal. So if the system were symmetric, then we would be lucky, because then everything that we learned from how the system responds to emissions, we could translate that into the response to removals. But we'll see that unfortunately things are not symmetric for a number of reasons. Also, carbon dioxide is not the only aspect through which these methodologies affect climate. So if we think, for example, about land-based methods, they also alter the surface energy balance through changes in albedo, in evapotranspiration, and energy fluxes, which can have effects beyond those of carbon dioxide. And then I'll conclude by reflecting on some of the implications for net zero. Good, so let's start with how the carbon cycle responds to CDR. So in this upper row, these pie charts, they illustrate the 3 carbon pools in the short-term carbon cycle. Okay, so these are the pools that are relevant on human time scales of decades to centuries. So this is the land, the ocean, and the atmosphere. So what we're currently doing is we're digging up fossil fuels from the geologic reservoir and releasing those emissions into the atmosphere. So what we do is, by adding additional emissions from the geologic reservoir, we're increasing the size of the pie, as is indicated here to the right. And what this does is it induces flux or a repartitioning of the carbon dioxide between the different pools. So currently what is happening, we emit carbon dioxide into the atmosphere, but then about only half of it stays in the atmosphere, and the other half is taken up by things on land and in the ocean. Okay, so that is that repartitioning. So not all of it stays in the atmosphere, but half ends up in the land and in the ocean. So now when we do carbon dioxide removal, so here the 2 examples that are provided are those that store carbon dioxide in a geologic reservoir. So this could be direct air capture or bioenergy with carbon capture and sequestration. We're taking carbon dioxide directly out of the atmosphere, or taking it out of the atmosphere and storing it in a geologic reservoir, or indirectly, if we do BACs mediated by the land. And so what we're doing is we're shrinking the total amount of carbon that is available in the short-term organic carbon cycle. And now what we do have is a reverse effect. So in sort of through the same processes that remove carbon dioxide when we add carbon dioxide to the atmosphere and repartition them to the land and the ocean. Now we have an opposite effect, by which if we take carbon dioxide out of the atmosphere, we have the land and the ocean that actually compensate for some of that loss. Okay? So there's sort of the idea is that it's a similar process as is occurring currently, but in reverse. And so this is known as the rebound effect. And it is illustrated here for a series of Earth system models. So in these model simulations, 100 gigatons, so this corresponds to 317 gigatons of CO2 are taken out of the atmosphere. Maybe to put this into perspective, this is about removing 10 times current emissions from the atmosphere. So it is a relatively large amount. Again, in these scenarios, the amount of carbon dioxide removal ranges somewhere between 100 and 400 between presently and the year 2200. So it is a relative significant amount. It is, however, at the lower boundary of what we can detect in these Earth system models. So how does the system respond to that? So if you look at the concentration of carbon dioxide in the atmosphere, you will see that as we remove carbon, you see a quick drop here at the beginning, but then carbon in the atmosphere rebounds. So, and the reason is that both the land, which is shown here in the middle, and the ocean do return some of that carbon dioxide to the atmosphere. So that after, let's say, 100 years, only sort of a fraction of the carbon dioxide that we have removed stays out of the atmosphere. Okay, so part of that will have been replaced by carbon from the land and from the ocean. And so the question really is one of the question is, how much of the carbon that we remove actually stays out of the atmosphere, which is a measure of the effectiveness of carbon dioxide removal. So, and also the other question is, how do we quantify it? Because we'll see that it's actually not that easy to quantify what the effectiveness is. And some of the simulations that I will be showing that originate from the publications in my lab, those are simulated with what is called an Earth system model of intermediate complexity. So it is a model that couples the entire Earth system and sits between these very complex Earth system models and then these zero-dimensional models or climate emulators. So this is geographic explicit. It has a three-dimensional ocean circulation, but is very simplified in the atmosphere. So it does represent the key Earth system processes that are relevant for these questions, including permafrost carbon and permafrost areas, but is computationally cheap enough that we can use it to run sensitivity experiments and explore hypotheses. So back to this question, how much of the carbon dioxide that we remove through CDR actually stays out of the atmosphere? And one complication in answering this question is that we're currently in a transient state. So we have emitted carbon dioxide into the atmosphere, concentrations are changing in the atmosphere, the temperature is changing. So now if we go to let's say, a state with net removal, the system will not only respond to that removal, but because of inertia, both in the carbon cycle system and the ocean system, it will continue to respond to the prior carbon dioxide emissions. And this is illustrated in these model simulations here. So these are idealized scenarios. So the blue one, this is this is from a transient trajectory, and then a 100 again gigaton carbon dioxide removal. And what you see here is that, in contrast to what we've seen before, is that the concentration in the atmosphere keeps declining. Whereas if we apply this removal from a situation of equilibrium, we see this initial drop and then this rebound that we saw earlier. So what this is, and And this is mostly due to the response, again, of the land and the ocean. So what we see is that the carbon cycle response is fundamentally different, whether we apply CDR from a transient state or from a state at equilibrium. This makes it very tricky to define what the what the effectiveness of carbon dioxide removal is. And just to illustrate this, if as a measure of the effectiveness we take the fraction that stays out of the atmosphere. Okay, so how much of those 100 gigatons of carbon remain out of the atmosphere after, let's say, 100 years? Then if we calculate this for the simulation with CDR applied from an equilibrium state, then the answer is half, so 0.5, which makes sense. So this is what we would expect based on the response to positive emissions. But then if we apply this measure to a simulation with the transient initial state, it's actually 2. So we're removing, so our atmospheric CO2 drops twice as much as we actually removed from the atmosphere. Okay, so that already illustrates the problem here. So why is that? The reason is that the ocean, even after we remove carbon dioxide from the atmosphere, continues to take up carbon in response to these prior positive emissions. So it will take the ocean a very long time to actually shift from a sink to a source of carbon dioxide removal. So it continues to take up CO2, maybe sort of giving us the illusion that that the carbon dioxide removal is very effective, but it is the delayed response to the prior positive emissions. So how do we get around these problems? There are, I would say, 2 main metrics one can define to calculate the effectiveness of carbon dioxide removal. One would be the same metric that is used to calculate what is called the cumulative airborne fraction. So the cumulative airborne fraction is the ratio of change in the carbon burden in the atmosphere divided by cumulative emissions. Okay, so it's basically the fraction of carbon dioxide emissions that remains in the atmosphere. So we can define something analogous, which is the cumulative removal fraction, which gives us the fraction of carbon dioxide that remains out of the atmosphere after removal. Okay, the problem with this is that it only works if we apply this metric from a state of equilibrium. So another measure that has been proposed is called the perturbation removal fraction. And here the idea is that this is now the airborne fraction of the perturbation. And so to calculate this, we need a reference simulation without carbon dioxide removal, and then we can calculate what is the airborne fraction of this perturbation relative to our reference state. Okay, so this is called perturbation removal fraction. The 2 metrics, they are identical when CDR is applied from a situation of equilibrium, because then this this reference change would be 0, and so then we recover the same relationship. Okay, so let's look at what we get. So in these simulation here specifically, again, we apply carbon dioxide removal from a situation of equilibrium, so that way we can apply the cumulative removal fraction. And here at the top, again, we have the changes in atmospheric CO2. In the middle, the land response. At the bottom, the ocean response. And as you can easily see, the amplitude of the carbon cycle response increases with the amount of removal. So I would say that is expected. So now the question is, what does the ratio look like? And so we can look at this 100 or 1,000 years after the removal. And so this graph here shows the removal fraction, which again is the amount of the total carbon removed that remains out of the atmosphere. And these yellow stars, these are for 100 years after the removal, and this is shown as a function of the amount of removal. So we see that there's a relatively strong dependence on how much carbon dioxide we actually remove from the atmosphere. So for 100, it's a little bit more than half, but then let's say if we go to 1,000, which is a fairly big amount, and outside usually of the amount of removals in scenario, we see that it is just a little bit over 0.4. Okay, so the amount of the fraction of the CO2 that we remove that remains out of the atmosphere decreases with the amount of removal. So this, you may ask, is this the case in other models as well? And that is actually the case. So here, this bottom panel, these are simulations with the Hadley Center Simple Climate Carbon Model. And it shows this, in this case, it's actually the perturbation airborne fraction. And then as a function of the cumulative emissions in the scenarios from which the removal is applied. And what we see is, so these symbols here, these are different amounts of removals, whereas these states here, these are different initial states of removal. So what we see is that there is a weak dependence on the amount of removal and a fairly strong dependence on the amount from which the carbon dioxide is removed. Okay, so this suggests, for example, that if we remove carbon dioxide from a scenario with a relatively low concentration, then the removal fraction actually decreases. Okay, so less of the carbon dioxide remains out of the atmosphere if we apply that from lower initial states. So So what we learn from this is that, first of all, only a fraction of the carbon dioxide that we remove from the atmosphere stays out of the atmosphere. And this fraction is strongly dependent on or weakly dependent on the amount of removal, but very strongly dependent on the state from which the removal is actually applied. Okay? So now you may object and say, well, who cares about carbon dioxide in the atmosphere? What we're really interested in is actually temperature, because that's really what's driving some of the impact. So the question is, how do we quantify the effectiveness of carbon dioxide removal in reducing temperature? So here again, we have the same problem, that we're in a transient system. So if you apply negative emissions from a transient state, then again, you get the response not only to your removals, but also to your prior trajectory of positive emissions. And this is illustrated in these graphs here. So this is temperature as a function of cumulative emissions for a scenario with the symmetric increase and then decrease in the atmospheric CO2 concentration. And so what you see is that even though the concentration trajectory is symmetric, what you get is an asymmetric response, or you get a hysteresis or a path dependence in your system response. And again, here on the left, this is the case for this model of intermediate complexity that I showed results from on the previous slides. And here on the right, this is actually with Earth system modeled. So we see that once you reach peak carbon dioxide concentrations and you're coming down, then there is a hysteresis in the temperature response, which again is caused by a delayed response to the prior positive emissions. So then the question is, so how do we quantify then the effectiveness of carbon dioxide removal under consideration of this lagged response? And one metric, which I call here the transient climate response to removal, in analogy with the transient climate response to emission. So this would be the temperature change in response to, or in our simulation, and then subtracting the lagged response, and then again divided by the total amount of removal. So what we're doing is we're trying to isolate the response to negative emissions from the total response to both negative and positive emissions. And for example, this lagged response here, this could be what is called in the climate science literature the zero emission commitment. So that would be the warming commitment that you get when you set emissions to zero. So that's one possibility to define this. Another way, again, is you could apply a removal from an equilibrium, from a state of equilibrium, in which case your lagged response is zero. And so then the relationship is simply your temperature change over the cumulative amount of removals. That would then gives you how much cooling you get per amount of removal. So if we do this, again, for the same simulations I just showed, so this is carbon dioxide to the left, which we already looked at, and then on the right, this is the temperature response. This is what we would expect. So there's this relatively, or there's this very abrupt cooling, and then what we see is that the long-term warming is approximately proportional to the amount of carbon dioxide removal. So this is what we would expect from in a symmetric system, where the system responds to removal in a similar way as it responds to emissions. However, what we also see is that there are small differences. So again, this is now this cooling effectiveness metric, so cooling per cumulative removal, which is shown here on the vertical, then again as a function of the amount of removals taking 100 years after the removal. These are these blue stars here. And so we see that there's a little bit of sensitivity to the amount of removal for smaller amount of removals. But for larger amount of removals, this effectiveness is relatively constant. So again, sort of this is consistent with this path independency of the transient climate response to emissions under positive emissions. What we see, however, is that there is also, in the case of temperature, there's a relatively strong state dependence. So if you apply a certain amount of removal, in this case 100 gigatons of carbon, then your cooling effectiveness depends very much on your initial state, and actually quite strongly. And this effectiveness decreases with increasing amount of atmospheric carbon dioxide from which the removal is applied. So to summarize this portion here, only a fraction of the CO2 that is removed by CDR remains out of the atmosphere. The removal fraction is dependent on the amount of removal and also on the background atmospheric carbon dioxide from which the removal is applied. And the cooling effectiveness, which is a measure of the cooling that we get per unit removal, is largely independent for removals in excess of, in this model, 500 gigatons of carbon. And we also see that this effectiveness decreases with increasing background atmospheric CO2. So so the question is why? So why does this matter? So let's say as you're considering a project, and with the given potential of carbon dioxide, and so you know that your potential, your removal potential is X, and then maybe by multiplying with the land surface that you have available, if you're going for land-based CDR, you know that the amount of carbon dioxide that you can sequester in your carbon dioxide removal project is a certain amount. And then these effectiveness metrics then allow you to translate what the effect is on the atmospheric CO2 concentration and also on temperature. And a mistake that is often made, especially in non-science circles, is to assume that the amount of carbon dioxide that is sequestered by CDR is the same effect on the atmospheric carbon concentration without applying this removal fraction. Okay, so again, only about half, and then depending on the state of the system we are in, of what we remove actually remains out of the atmosphere. So when we convert potentials from CDR project into effects on atmospheric CO2 concentration, then this is something we need to take into account. Another question you may ask, well, so we know, we sort of know these things from carbon cycle science in response to positive emissions. So can't we just assume that the system is symmetric and apply all these quantities, all these metrics to the response of the system under removal? So this is really the question about asymmetry. So what I mean by asymmetry here is that when the driver is symmetric, so let's say our emission trajectory is exactly is equal and opposite to our removal trajectory, is the carbon or the Earth system response, is it also equal and opposite? Okay, so again, maybe I'm going to use this figure here to illustrate this again. So here we have a symmetric pathway of carbon dioxide increase and then decrease, and yet our temperature trajectory is not symmetric, it's asymmetric. And there are different reasons for this asymmetry. One we talked about already, it's this lagged response, so the inertia in the ocean and in the climate system. Which we try to correct for when estimating the effectiveness of carbon dioxide removal. But there are also some other potential sources of asymmetry, which have to do with the timing between emissions and removals, right? I would say that the most, or in most scenarios, the removal lags the emission. So what this means is that the emission and the removal are actually applied from different states of the climate system. Because as you keep emitting, your concentration increases, your climate warms, and so we saw these state dependencies. So if there's a time period between an emission into the system and a removal, then you could expect the state dependencies to play a role. However, there may also be effects that arise because of nonlinear carbon cycle and climate effects. So one nonlinear process, for example, is the CO2 fertilization effect. So the amount of carbon dioxide or the rate of photosynthesis in some ecosystems is found to have a logarithmic relationship with the concentration in the atmosphere. So if you have a logarithmic curve and you're in that domain where the curve is nonlinear, then actually whether you go up, which means you increase your CO2 concentration, or you go downward, will give you different effects, okay? And this is independent of the timing between emission and removals. It only arises because you have these nonlinear effects in the climate system. And so by running very similar simulations to the ones I showed before, so we again have these instantaneous removals from the atmosphere, and then we have instantaneous emissions of the same size. So here in this graph on the right, these are the emissions, and this shows the fraction, so the airborne fraction, the fraction of emission that remain into the atmosphere, and here to the left, this is the fraction of removals that remain out of the atmosphere. And here, this is the zero line. So if you would expect the system to be symmetric, the two sides should be mirror images of each other, right? So you would expect for example, for this case here where emissions and removals are released at concentration, which is double the current concentration, you would expect these to go up. Instead, they go down. So this is an indication that there is asymmetry in the system. And this comes very largely from these nonlinearities in the ocean and land carbon cycle response. Again, is this a thing of this particular model? And the answer is no. We do have climate model data from these complex Earth system models that also ran simulation with an instantaneous 100 gigaton emission and removal from a pre-industrial state. And these are these triangles here. So again, this is the fraction that remains in the atmosphere for emission. Here to the left, this is the fraction that remains out of the atmosphere after removal. And again, what we see is that there is asymmetry. So this seems to be a robust feature in these Earth system models. And the asymmetry here is on the order of 2 to 9%. So what this means is that we cannot reasonably apply the airborne fraction or the amount of, or the fraction of carbon dioxide that remains in the atmosphere under emission to the fraction that would remain out under removals because of these asymmetries in the system. So if we, which according to these model simulations are on the order of up to 9%. So again, then the question is, well, how does this look like in terms of temperature? So this is here shown to the right, and we see that that as we would expect, the system is more symmetric. So the temperature response to an emission and the removal is more similar than what we get for carbon dioxide removal, but it is not exactly the same. So we still do see a slight asymmetry in the system. And again, this is not model dependent. We do have from these same Earth system model simulations, we can calculate the temperature anomaly that you get for a 100 gigaton emission and removal. And the warming to the emission is shown here in red. The cooling to the removal is shown here in blue. So what we see is that for some models, in averaged over year 70 to 100 after the removal or emission, the warming can be larger than what you would get, or the cooling you would get for an equivalent amount of removals. Or if we go to this model here, the asymmetry is actually the opposite. So we get a stronger cooling than we get warming. So what we learn from this is really that in terms of temperature, the asymmetry varies between models. So the sign of this asymmetry is uncertain. So to briefly summarize, what this indicates is that the carbon cycle response to carbon dioxide emissions and removals is asymmetric, and the temperature response is also slightly asymmetric, but there's very low confidence in the sign of the asymmetry because we have models going in either direction. So this requires more exploration. Okay, so this was very much carbon focused. However, carbon dioxide, not all, but some carbon dioxide removal methodologies also affect the climate system in other ways. And this is summarized in this complicated figure from the Working Group 1 report of the IPCC. So here on the left-hand side, these are the different CDR methodologies. They are here organized by the time scale of storage, ranging from short time scale of storage to geologic time scales. And then if you go to the middle of this figure here, you see that many of these methods do have other effects on the Earth system other than carbon dioxide removal. So for example, if we're looking at forest-based methods, afforestation, reforestation, forest management, then they could either result in an increase in nitrous oxide emission or a decrease, potentially an increase in methane emissions. Decrease in methane emission and increase in these biogenic volatile organic compounds. So these are also, so nitrous oxide and methane are also greenhouse gases. So by deploying these, some of these CDR methods, we on one hand, we sequester carbon dioxide, but we may emitting other greenhouse gases into the Earth system. Also, and this is true for non-geologic methods, because we affect the Earth surface, again, by planting trees or by cultivating certain crops, we do influence the albedo, which is the reflectivity of the Earth system. And at the same time, trees are taller than maybe grasses that they replace. So they affect what is called the aerodynamic resistance, which then affects the fluxes of latent heat and sensible heat. So by modifying the Earth's surface through these carbon dioxide removal methods, we can also expect to see so-called biophysical effects, which are related to these changes in albedo and evapotranspiration and so on. They can actually be quite significant. So this figure here illustrates the biophysical effect of afforestation and reforestation. So what this map here shows is, so in yellow, these are world regions where planting or replanting trees has a synergy with the removal. So it means that the biophysical effects enhance the climate effect of the removal. But then in other regions, especially at northern latitudes here, they actually work counter the removal. And these pinkish areas, these are regions where the biophysical effect of reforestation or afforestation counters the sequestration effect from planting trees during the winter months, so especially in a season where there is snow cover, because this snow enhances the albedo effect of planting trees. So I think this is something we all know. If we look at the forest in winter, it is still very dark, whereas if we look at the grass or at the field, it is white. So it's not masked by trees. This is why this effect is particularly strong in the winter. So these lines here indicate the most southern latitude at which the median biogeophysical effect counteracts the sequestration effect of afforestation. And then these darker brownish dots, they show where the biogeophysical effect counters the biogeochemical or sequestration effect during the entire year. So what this indicates is that in these latitudes, these biophysical effects oppose the climate effect of carbon dioxide removal, and in some, especially at high northern latitudes, to the effect that they actually negate the effect of carbon sequestration. So by planting trees, removing carbon dioxide, but through the biophysical effect, sort of in higher northern latitudes, we could end up with the net warming effect. And so these are effects that are seldom considered in accounting systems that look only at carbon, but not at these other effects. Another very important consideration is the vulnerability of carbon stocks to disturbance. So so especially for carbon dioxide that is stored in in biomass or in above ground biomass or upper soil layers, this carbon may be vulnerable to disturbance. And this map here shows the disturbance or the return interval of natural disturbances that replace stands in those forests. And what this study here found is that the biomass dynamics of 44% of forests globally is strongly sensitive to stand replacing disturbances. So this means that if we plant a forest in one of these areas, there is a risk that this forest might be disturbed by wildfire or by insects, and the carbon dioxide then returned back into the atmosphere. So this does not consider anthropogenic disturbances, but those exist as well. So land use change decisions can be reversed, so that land that was designed for forest is then later deforested again. So again, there's a risk that above ground biomass is vulnerable to disturbance. And the reason this matters is especially if you use these above ground biomass to compensate for a certain amount of fossil fuel emissions, for example, then even though you may be compensating at the time of when your forests grow, at the time that the carbon is re-released into the atmosphere, you would have net emissions into the atmosphere, which would lead to additional warming. So so re-releasing carbon or temporary carbon storage or impermanence leads to higher cumulative emissions and higher temperature after the time of release. Okay, so what are the implications of these considerations for net zero? So I'd like to illustrate this by using the concept of carbon neutrality, which is very closely related to this idea of net zero CO2, which means that a given amount of carbon dioxide that we emit into the atmosphere is balanced by the same amount of removal, so that the effect is the same as avoiding an emission. Okay? So now the question is, if you're carbon neutral, how does that translate into climate neutrality, which then here is defined as, or a system is defined as, here in this case, as climate neutral. So I'm saying in this case because there are many definitions out there, but the way I use it, a system is defined as climate neutral is if the climate outcomes of emission and removal are the same as the climate outcomes as an avoided emission. Okay? And so this now becomes more complicated because when, let's say, we emit carbon from fossil fuels, not only do we emit carbon dioxide, but we emit other greenhouse gases as well as aerosols. So it's not just carbon dioxide, which is in the equation, but we have other greenhouse gases and aerosols as well. So now if we look at the removal piece here, so we're removing carbon dioxide, so that is the intention, but then on the way we may be producing other greenhouse gases, so which I showed with the example of forest-based methods. There may also be these volatile organic compounds that are emitted, which have an effect on cloud cover, for example. Then we looked at these asymmetry effects and also at biophysical effects. So we have a whole range of different effects that carbon dioxide removal has on the Earth system. So really the question is, if we compensate for unit emission from fossil fuels, let's say by sequestering the same amount of carbon dioxide with some form of land-based removal, do we end up with the same temperature. And sort of the question is likely not if we do not consider these other effects, right? And sort of if, from an Earth system perspective, this so one way to picture is that extracting coal or gas or oil from a geologic reservoir, which is removed from the short-term carbon cycle, releasing that into the atmosphere along with co-emissions, is a fundamentally different process than if you now alter the land surface to capture that carbon dioxide. But in the way, again, you're emitting other gases, you're modifying the land surface, you have symmetry effects, and plus your storage may not be permanent, right? So even though you may be carbon neutral because you have offset that one emission, that unit emission with the same amount of removal, you may not be you may not be climate neutral if you do not consider these other effects into account. And we did run some idealized model simulations to illustrate this, again, with our model. So here we have an idealized emission scenario, which is indicated as a baseline. So this, as the red baseline here, so these are historical emissions. And then we, after reaching peak emissions, we decarbonize, reaching net CO2 emissions around mid-century, and then going net negative. So this is our reference case. So now we constructed a series of other scenarios where we allow for additional fossil fuel emissions and offset those additional fossil fuel emissions with reforestation or afforestation. So by definition, what we end up with is, again, in terms of emission, the same baseline. Okay, so we allow for additional emissions, which we now offset with removal through reforestation. So by definition, these scenarios are carbon neutral. So the CO2 emission trajectory is exactly the same as in the baseline. But then if we look at surface air temperature, we see that at the time of peak, so here, which is the time when emissions reach net zero, there is a non-negligible effect on peak warming. So these different colored lines, they illustrate different effects. So for example, the biophysical effects from reforestation, this is shown here in the blue. So this difference here between the baseline and the blue line at the peak, this would be the effect, the biophysical effect of planting trees. So here deliberately I didn't put any numbers, because it's idealized. So far it's only one model, but it is and in our model it is on the order of 0.1 degrees Celsius, which is on the order of some of these other effects. The impermanence, the effect of impermanence, is illustrated by this green line here. So here it is assumed that after the peak, the carbon that was sequestered in those forests is re-released into the atmosphere. It's a relatively drastic scenario. We assume that all of the carbon is re-released, but what you see here is that in the long term, so depending on when the re-release occurs, in this case it's after the peak, but by the end of the century, you again end up with additional warming. So what this illustrates is that these non-CO2 climate effects of CDR result in higher peak warming relative to the baseline. So what do we conclude from this? That it is crucial to consider the full climate effects of CDR. So we need to move beyond CO2, but also beyond greenhouse gas neutrality, and consider these other effects of CDR to make sure that in pursuing a net zero strategy, we actually do not fall short of our climate goals. And many of these climate effects of CDR are poorly constrained currently. So I think we reforestation, afforestation is relatively well studied, but some of the other methodologies in the ocean, but also things like biochar BECCS with specific crops, the biophysical effects, and also the non-CO2 greenhouse gas effect has been is poorly quantified. So what we need is really more research into the non-CO2 effect of these CDR methodologies. And as in many other fields, so for example, the biophysical effect of afforestation is something that has been known in the scientific community for 20 years now, and that's when the first papers quantified this. And yet it has not yet trickled into the policy community and the, let's say, the consultancy industry that actually develops these protocols. So we need to strengthen the science policy link and make sure that the accounting systems that are developed to ensure net zero are strongly based in science. So I'll conclude here, and I'm happy to take questions. Thank you.
Thank you so much, Kirsten, for a brilliant overview, and I think you've really explained well how carbon removal is in these pathways to achieve our climate goals, but thinking through the implications of that is not simple. We've got just under 20 minutes for questions. I hope you don't mind, since I've got the microphone. I'd love to ask you a quick one, which is you motivated the talk throughout with results from yours and other complex Earth system models, but then right at the start you showed these stylized pathways. And generally, the way that the consistency of those with sort of Paris Agreement is calculated is using very simple climate models. So given all these complexities you mentioned about impermanence, biogeophysical effects and things, to what extent do you think those are captured in these simple models that are actually often used to work out the consistency of pathways?
So that is a very good question. So in simple models, the carbon cycle is often fitted to similar experiments where you release a pulse of carbon dioxide into the atmosphere, and then you look at how how the response evolves over time. So generally with 3 different time scales, and so what we show is that the system is asymmetric. Right, so those same coefficients on those different time scales, they would not work in the same way if you have a removal of carbon dioxide. So I would say sort of the question is out there. So these simple climate models, I think, have been validated relatively thoroughly for physical metrics, but they have been validated relatively poorly for carbon cycle metrics. And so I think there's a paper right now under review, but we really need to understand how these models perform, especially in emissions where carbon dioxide and temperature peaks, and then the system recovers from that. Yeah, but I would say based on these results, the fact that they are fitted to the response to emission is likely to introduce some errors.
Great, thank you. We have a couple of mics around the room, and so don't be shy in putting your hand up if you have a question. I see one question over here, so if we could get the microphone to you. Thank you, Heather.
Hi, Andrew Lockley. These models, as pointed out, are not necessarily very sophisticated in terms of the carbon cycle, and they also don't agree. So I think quite a number of people might be fairly sceptical about the reliability of the results. And one way that could be tested is by looking at isotope fraction to try and trace carbon as it moves through the carbon cycle. So is there enough I know the fossil isotope fraction is very different from the atmospheric isotope fraction, but is the ocean fraction and the atmospheric fraction different enough that we could effectively track carbon as it moves between the three reservoirs, so that we could actually try and validate these models experimentally? Because without that experimental validation, with the degree of disagreement, they just don't seem to be confidence inspiring.
Yeah, so I think there are only very few models that do incorporate isotopes in the model. So that's I think that has. So my understanding is that isotopes would be helpful to constrain the time scales of carbon exchange between the different reservoirs. So often what is used for validation instead is using observables of the current evolution of the climate system. So there are estimates of fluxes of carbon dioxide between the atmosphere and the land surface, or between the ocean and the atmosphere, that are provided annually with an uncertainty range. We can also measure, based on our emissions estimate, again, the fraction of carbon dioxide that remains in the atmosphere. So these are the metrics that are used to validate those models. I know that groups, especially those interested in paleo applications, they also run models with isotopes. But I think so as far as I know, none of these complex models does include those in the carbon cycle. It is often models of intermediate complexity. But as far as I know, they haven't been used to validate the carbon cycle. That what is used there is observable quantities other than isotopes.
Any other questions? We have one there, and then one back there afterwards.
Hi, Kirsten. Thanks for the great talk. I promised a difficult question, so I'll do my best. This is two-part. First one's just a quick clarification to make sure I understood the plot. So can you go to the plot with the transient and equilibrium simulations?
Yes.
So if I understand this correctly, for the transient simulation, did you run emissions up to the point of net zero and then apply the removal?
Now we ran to a point of 2 times carbon, so doubling of the atmospheric CO2 concentration, with this sort of idealized 1% scenario. And whereas in the equilibrium case, what we did is we spun up the model, so we ran the model to equilibrium with that same concentration.
So then my question is, did you differentiate the impact of the pulse from what would have happened in a transient scenario where there was no removal? Basically, my question is, did the removal increase or decrease the slope of the blue line? Because to me, in my head, I would imagine that it would decrease the slope, just based on what you showed in your equilibrium results. Is that right? Is that sensible to you?
Well, sort of the way to picture this is when you're in this transient state, right, the ocean is still removing or still absorbing carbon because it hasn't realized that now we're on a downward concentration trajectory. So you have the ocean that is sort of that is still in sequestration mode. So in a sense, it's reacting in the opposite direction than you would expect from the removal, where you would expect now the ocean to be a source of carbon dioxide to the atmosphere, right? So that's why you get this large efficiency here of 2, because your carbon dioxide in the atmosphere decreases not only because you've removed carbon deliberately, but also because the ocean is still a sink and still sequestering carbon from the atmosphere also.
So maybe just asked a slightly different way.
So sort of it's reinforcing the removal.
It's reinforcing the removal.
Yeah.
Okay.
Yeah.
Thank you. Very helpful.
And there.
Hello. Thanks very much for your talk. I was sort of slightly struck and slightly surprised by the fact that lots of your simulations are concentrated on the effect of a pulse of removal. Because it seems to me that if we're going to have any impact, we need to have continual removal, particularly if we're going to have continued emissions. And it also seems quite unrealistic to think that we're ever going to have a pulse of removal. So could you comment on why you chose to look at that, and what happens if you assume some sort of continual removal?
Yeah, thanks for bringing that up. I should have justified that. So these pulse emission, so pulse removals mimic these pulse emission simulations, which have been used in carbon cycle science to understand the carbon cycle response to emissions. So quite a bit of our understanding is based on these pulse emissions. So this is one reason. The other reason is that at least qualitatively, and in the case of temperature, so quantitatively, the response is largely independent of the pathway. So for temperature, you would expect your response to be approximately the same as in a scenario with continuous emissions or removals. So just to give you an illustration, the only, maybe moving to temperature, right, sort of one artifact of the pulse may be this relatively sharp drop in temperature at the beginning. But let's say if you're interested in time scales over here, then you would expect the response to be the same if you have a trajectory of gradually increasing emissions or removals. So again, because the system is largely path independent, or the response is largely path independent, it does not matter what rate of emissions or removals you apply.
Any other questions? Excellent, we've got one down here, yes. Just right down at the front here, Tristan, thank you. Don't be shy. If you have a question you're not quite sure whether to ask it, wondering if it's crazy or insightful, do put your hand up and ask, because even if it's crazy, perhaps 5 other people in the room were wondering the same thing. So,
does the rebound effect imply that conservation of these pre-existing landscapes, these marine and terrestrial carbon sinks, is like a must? Because if we were to increase the amount of planting of newly developed areas, that rebound effect kicks in. And if we let these existing areas decline, that's urbanization, that's agrarian development, that's industrial activity, which all contribute to carbon outputs that exacerbate the rebound effect. What are your thoughts on this matter?
Yeah, well, I don't think the rebound effect would be an argument in favor of conservation. It is, I would say, it's more of an accounting metric, right? Sort of if you, let's say you decide to protect a stand of forest in a given area, which you know stores this much carbon, then, and you're counting, if you're interested in how much carbon dioxide you will avoid being emitted or into the atmosphere, and then what the effect is on carbon dioxide, that's when this rebound effect plays a role. But I don't think that it matters in terms of an argument for against forest conservation. It's more how the carbon accounting is done in those cases.
Thanks, Kirsten, for a really great talk. Given the secondary effects that you mentioned, and acknowledging that we don't know as much as we'd like to, do you have a favourite CDR method? Is there a better method than others?
Well,
I'm asking you, not Miles.
Yeah. Well, I mean, I concur. So these land-based methods are problematic for many reasons. There is, there are the biophysical effect, there are the permanence effects, but then land has many uses. So land use competes with food production, and so finding the land to do these methodologies at the large scale is a challenge. In the ocean, I would say we don't really know what we do when we interfere with the ocean. So I think many of the effects, such as alkalinization, CO2 iron fertilization, can have many unintended effects on the ecosystem. We don't understand the permanence of these systems either. So I would say, in terms of unintended consequences, these can be risky. So the technology I would say that has the least effect on other effects on the Earth system is probably direct air capture. But there are, I mean, many other socio-technical problems, sort of costs, and developing the technology to scale. But I would say in terms of Earth system impacts, that looks like the most promising. So I think you're probably pleased.
A good one to discuss over a drink later on, perhaps. We've probably got time for one more question, if anyone would like to ask one. If we got a hand up there? Yes. Tristram, can you see just... Oh, sorry. Yeah, I'm making you do all the walking this time.
Yeah, so it's probably basic to your talk, but did you really say that reforestation is causing increased CO2? Or did I get that wrong?
Increased temperature.
What?
Increased temperature.
So the
at northern high latitudes.
So the temperature models that you'd shown, you mentioned that they showed contradicting results. Was that relevant to that, or was that not relevant there? And even the increased temperature, I didn't quite understand that about how snow makes that happen.
Yeah, I'm happy to explain this again. Is that the slide you're referring to? Yeah. Okay. So when you plant trees, so first of all, they're darker than maybe the grassland or the bare soil that you replace. So they absorb more incoming solar radiation than, let's say, the type of land surface that you had before you planted the forest. Also, trees are taller than grasses, so they have what is called aerodynamic resistance, which causes turbulence and contributes to these fluxes of sensible and latent heat at the Earth's surface. And but you sort of usually evaporation, sort of increased evapotranspiration, which you would expect has a cooling effect. So you have a tension between decreased albedo and increased evapotranspiration. And sort of how that plays out, that depends on your latitude. Yeah. Because in winter, the trees mask the high albedo of snow. So this is what I was trying to explain. So if you have snow that falls on a forest, the forest is still very an seen from the atmosphere. So it still absorbs a lot of incoming solar radiation relative, let's say, to an area with sparse or very short vegetation, where the snow seen from above will actually appear very bright. Okay. So there's this balance between increased evapotranspiration when you plant trees and decreased albedo. And how that balance plays out, that depends very much on latitude because of snow cover. But at high northern latitudes, the increased absorption of solar radiation wins. And this is why you could end up with a net warming effect.
So the overall confusion that we have about how all of this affects temperature of the Earth is probably partly to do with the temperature varying even in different levels of the atmosphere, we don't seem to know about what it's really doing to the temperature. But you're saying that in the localized areas of where trees are, you can see that the temperature does go up. But overall, does that also affect the whole world's temperature, or we don't even know? I think we don't know.
Well, I mean, sort of the first sort of point I try to make is that often we do not consider these effects in when we talk about reforestation, right? Sort of. So what we tend to look at is how much carbon dioxide do trees sequester, and then sort of we use that as an offset or as a removal. So we don't really think about these additional climate effects. So I think that is one problem. The other problem is that these biophysical effects are poorly quantified. So they're very local, very regionally specific. You can model them in these type of Earth system models. You can also do this through remote sensing. So you can use satellite data and compare, let's say, areas with trees and without trees, and then look at the different fluxes, but that doesn't really tell you how that changes in a changing climate, right? This would be only under the current climate state. And then the third problem is then you need metrics to convert those biophysical effects into a CO2 equivalent, which is also tricky to do. So we know these effects are out there. I think we understand the balance. We know that in the tropics, likely biophysical effects will amplify the benefit of planting trees, whereas at higher northern latitudes, they will oppose that. So I think that we know. We don't know where the exact boundary is, and potentially what exactly the offsetting effect will be.
On a simple...
Sorry, the good news is there's more opportunity to discuss this over drinks and posters. So I'll hand back to Helen to explain how that will work. But finally, let me just say thank you once again, Kirsten, for taking it.
Thank you.